Good morning, and welcome to today's Oil and Gas Journal webinar, Finding Your Fit, How to Benefit from the Right End Connections, sponsored by Swagelok. I am Chris Smith, Oil and Gas Journal's Editor-in-Chief with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit any questions to the questions window, and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. And also, please be aware that today's session is being recorded and will be available on the Oil and Gas Journal website within the next 24 hours. You'll be notified by email when the archive is available. Now I would like to introduce our speakers for today's discussion. Matthew Messer began his career at Swagelok in 2013 as a computer-aided engineering analyst, supporting tube fitting development through finite element analysis and computational fluid dynamics. He then became a project engineer, providing quality engineering direction for in-source parts. From there, Matthew joined the new product development team as a design engineer, working on numerous industrial fittings-related technology and product development projects. As a senior design engineer, Matthew currently focuses on the creation of new industrial IoT products and mentoring junior engineers on tube fitting development, intellectual property, and technology road mapping. John Kestner began his career at Swagelok in 2009 as a technical inside sales engineer responsible for supporting general industrial multi-turn and spring-loaded valves. He then joined the field engineering team, supporting parts in North America with a focus on pressure regulation and analytical instrumentation. John has also managed the Swagelok regulator product line, worked as a field engineering supervisor, and served as a field engineering regional area manager. As a senior product line leader, John currently manages a team focused on providing reliable valves and fittings for industrial applications across oil and gas, chemical processing, clean energy, power generation, research and development, and many other industries. And with that, welcome, Matthew. Please go ahead.
Thanks, Chris, for the great introduction. So, as you know, the presenters today are myself, Matthew Messer, and John Kestner. Chris gave a brief introduction, so I'm going to kind of just glaze over these couple slides for us for the introduction for John and myself and get right on to the agenda. So what we're going to be covering today is understanding how to create a seal versus allowing permeation through your products, as well as understanding fitting design factors. That's going to include permeation, leakage, burst, vibration fatigue, and corrosion fatigue. John's actually going to jump in on part 3 for evaluating fitting technologies. And then I'm going to jump back in for part 4 for Swagelok tube fitting and kind of going through that. So part 1, creating a seal versus permeation. So what we want to kind of understand is what is a leak versus actual permeation going through a seal. So the two pictures at the bottom kind of show that gray material is a sealing mechanism, and then the black lines are kind of like your tube or something that's allowing the media to go through. When you're having a leak, what I'm going to call is a continuous pore structure, which is either an open pore path or crack that's allowing molecules to flow through. So in that left image, you'll see that there's a crack kind of in the middle of that sealing material where that material is allowed to go through, as well as in that upper kind of portion, you do see some other material going through that as well. This can happen between two mating surfaces or within an actual component itself. When we talk about permeation, happens, the seal is actually really good. It's able to block through but you'll actually get gas molecules that go through solid material. This is usually mostly concerned with soft materials or in gas applications. So some of the factors that drive permeation rates, some easily quantifiable ones are pressure, temperature, and seal length. And with pressure, it's a linear relationship. So a 10,000 psi gas will permeate exactly twice what a 5,000 psi gas will. For temperature, it's also linear, but it's with respect to absolute zero. So it's based on like 400 Kelvin is going to be permeating 33% faster than a 300 Kelvin gas. With seal length, you really want to increase that permeation length that you have when you're going through it. And that's because it's relative for a square root function. So if you're half as thick as another seal material, you're going to permeate about 44% faster. On the next slide, we'll talk a little bit more about seal material and gas, but those are really impactful variables, and they're kind of harder to quantify than those seal length, temperature, and pressure. So we want to kind of show this in this table format, which with nitrogen and nylon being a kind of a baseline. Think of these units as being something like SLPM or SCM, but we're just going to kind of leave a unit list to make it a little bit easier to show on the screen. With how these affect permeation, think about if you have like hydrogen with nylon, it's going to go 600 units faster than if it was a nitrogen gas. And that really matters when we're talking about how long it's going to take for you guys to lose gas rates and stuff through your material. And on the screen, you'll see as well, we have these little green boxes that say factors to consider when selecting a fitting technology. What I really want you to do is start to think about what do these factors do and how do they affect choosing a different fitting when you're going to size up a project for your applications. So for this slide, what we really want you to take away from is like how long of a permeation path does the design allow? Because with material and molecule, it really affects what that's going to look like. So on the next slide here, instead of being just permeation, we're going to talk about creating a seal, because before we talked about that there's a continuous pore structure that happens between mating surfaces. What we really want to do is eliminate that. And that's because when you have machined surfaces, they all have a degree of roughness. And within that roughness, those peaks and valleys can kind of mate up to create leak paths. And that's kind of can be a big problem when you're trying to create that seal and not allow media to go through those paths. So on the screen, we have 3 different images here. And that's just to show a representation of 2 machine surfaces that have kind of that roughness. So you have those peaks and valleys. We want to just kind of showcase that the different force levels that we have. If you have like a lower force, you're going to get very little deformation, or if none at all. And that kind of means that you're going to have very poor sealability, because you will get like gas molecules to go through those mated up paths. So you may need to require a lube to create a seal, which will eventually wash away either through just general general wear on the lube from the media that's passing through it. It'll eventually leak out. Now we'll go to the medium force side. That's usually deformation that's going to remain in the elastic region. So you're minimizing the damage. So you're going to create a higher cycle life. And that's really good for like valves that you'll see like those to be peak designs or something like that. So you can minimize the damage that occurs to those materials. So you see that seal range usually for softer materials, like I mentioned for peak or PTFE, those kind of things. When we talk about a higher force, you're really getting down to the deformation is going to be plastic, which is more similar to what you'll see in a fitting material, where you're actually going to be burnishing the pieces together and you're going to create a more reliable seal. This means that you'll most likely get lower remakes due to the permanent deformation, because you're only going to get that elastic degree back with the spring back that the material has. All right, we'll move on to understanding fitting design factors. So we mentioned before about various leak paths and how those are created. So the equation on the screen is for kind of a flow rate. We've modified the equation a little bit to kind of suit how this, for a valve, how it would work. So you'll see like in the valve stem area, you'll see H, which is kind of that little region there between the stem and the body. And that's like your zone where you're thinking about, and like when we talked about creating the two mating surfaces together and keeping them tightly together to create a seal. You also have that diameter also matters. That is that W in that equation. That circumference is really crucial. And then the cube function there, which is actually what really matters, is that H. And that's what we mentioned with that stem and body connection. We mentioned seal length as well, which is that L along the screen there. Elongating that out actually means that you will have less gas that can get through. That was that permeation factor on sealing length for the square root function. So one of the next things to keep in mind is having a burst rating on the fitting. That's because it's a mechanical failure, and it would likely mean that the fitting would no longer be usable after the fact. So when we talk about it being not properly designed, all the fittings that you buy should have a clear burst pressure that they will meet. Improper design will allow the fitting to burst below its rated pressure, which means it's going to be a weak point in your system. Usually the rating for the fitting is based on the tubing, so you really want the tubing to be the burst before the fitting failure. And you can kind of see that in the images to the right here. That's what we want to show here, that the fitting is not the failure point, but the tubing becomes the failure point. So some of the things that make it so that you may not be able to attain that burst pressure, it's usually going to be because it's not properly assembled. The fitting's rated pressure is dependent on proper assembly. And it is also, poor assembly can cause the fitting to be under tightened. And that means that you're going to have a lower assembly force. It also means that it's like, because you're not getting the proper tightening, that you could easily get a tubing blowout to occur. So one of the things to think about when choosing a fitting is how easy is poor assembly identified within the fitting, and how likely is that to occur. The next thing to keep in mind is actually vibration fatigue. So imagine this being kind of like a paper clip going back and forth in your tubing system. As you're bending that back and forth, the support along that bend is going to make sure that you're going to increase the cycle life of that vibration resistance in the fitting. The bending distance also matters, as well as the speed and the material properties. So if you're using a higher alloy strength fitting, you're going to get a little bit better performance there. So what this comes down to is there are industry standards that fittings can be tested to. And that is kind of controls the bending distance and the speed so that different fitting technologies can be compared against each other. So what we're kind of showing on the screen here is actually a fitting that's being tested. The test sample is there on the left side of the screen, and the right side is actually the vibration mechanism that's moving up and down to create that flexure in the fitting. And really what we want to make sure that you look into when just deciding a fitting is, how is the fitting being supported? How is the fitting technology being safeguarded against that vibration so that you can maximize your life of that fitting in your applications? Corrosion fatigue can be a major problem when you're looking at material compatibility in your systems, whether or not the material itself is of weaker a weaker alloy. So for example, one of the things I'm most closely related to is Swagelok's 316 stainless steel. What we do internally is we ensure that our chromium and nickel content for our stainless steel actually has a higher minimum than what the ASTM requires. And what that does for us is it means that we can have better corrosion resistance and stability of the material under corrosion for our applications. One of the big reasons corrosion fatigue is a problem is you can get areas where the corrosive media, whether it's internal or external, gets trapped. And that just means that the area where that is at, it gives the opportunity for corrosion to occur. So what we really want to keep in mind is there are areas that has the ability to be trapped. You don't want that to happen. You really want to maintain that your internal, external areas allows the media to flow around or in. I just want to give a couple of summaries here for you guys to consider. One, we talked about some of how long of a permeation path is allowed in the design. How much force are you putting into the seal area to maintain a seal? That's that minimizing the H, minimize that distance for the seal area. And then how long is it? That means maximizing the L, and we ensure that the distance that the fluid has to travel through is much longer. It means the pathing is more difficult. And then for the fourth one, how easy is a pour assembly identified with the fitting technology? And then how does the fitting design support the tube to maximize life and vibration rotary flex applications? And does the fitting design allow for corrosive media to remain trapped? And with that, we'll move on to part 3, which, John, you're going to be taking over.
Yeah, hey, thanks, Matthew. Hopefully everyone can see and hear me okay. I appreciate the lead in to a topic of really choosing what technology to use, right, is effectively what we want to get at with this section. We generally use a scale of kind of good, better, best, and that's not just for connections. That's almost everything that we look at in terms of getting into the right technology, whether that's a valve, a regulator, a gauge, a fitting. So that's the context we're going to use in this discussion as well. What we will do is we'll walk through about 7 different types of connection technology. It might feel a little bit like a walkthrough time. We're going to do them chronologically, at least in terms of technology is concerned, and what problem each of those connections really is trying to solve compared to its previous iteration. And then ultimately, the goal is to enable users and designers and engineers to go to bat with a full set of information to make the right choice of which connection technology works best for the particular application it's being used for. So with that being said, I will get into our next slide here, which covers tapered threads. So these are used very widely across many different applications and industries, whether it be fitting, a valve connection, regulators, you name it. There's probably some version that has a tapered thread, most common of which is the NPT thread. Tapered threads really work on the interference of the slight taper between the male and the female ends, facilitated by some sort of sealant, very commonly PTFE, that helps to create that seal, and as it's torqued down, really plays into creating a positive environment for sealing. So one thing about NPTs, as you can see, if you can make out the red line there, is that the length is actually very long. So that has a long permeation path, but Depending on what's used, PTFE tape, which is common, you will get some permeation through that path. The torques can also be extremely high, and probably the most problematic, at least when you think about using these practically in the field, and anybody who has gotten frustrated in trying to align a gauge that has an NPT end on it to look nice and neat the direction you'd like it to go, is that NPT or tapered threads generally aren't gaugeable. And so you will make them up by torque, but there really isn't a way to know exactly, is this fitting made up correctly or not, because it's not a position-based connection technology. So again, these are very common connection types used in many places, and even used successfully in many places. But it's really our most basic type of connection is the tapered thread. So as I mentioned before, we're going to evaluate these technologies on a number of factors that Matthew had outlined, and really the goal is to give a complete picture of what all the different technologies can do, and quite frankly, what they can't do. So tapered threads here, you see we've discussed really the fact that there is a permeation path. It's relatively long, so it's a bit in the middle there, but there is a permeation path. It does take high sealing forces. The sealing area is relatively large, right? But you don't get that gaugeability. There's really not a good way to make sure that it's assembled correctly. The flex support isn't great. One thing to note on tapered threads is that there is very little, if no, entrapment areas. So your corrosion performance is actually pretty good. There's really nowhere, as Matt described it, for that system fluid to stay stagnant and really do its work on the materials. So from that perspective, it's actually a pretty good technology for corrosion. So moving on, one of the technologies introduced to solve the problem of gaugeability, or being able to identify that a product was, a connection was made up correctly, is O-ring sealing fittings, right? And the same would go for a lot of gasket style fittings as well, right? Is that this allows the user to really identify that this connection is made up correctly or fully, and it's not reliant on just increasing the forces between the two tapered threads. Now, there are some drawbacks to this solution of gaugeability, in that O-rings, as Matt had described and you saw on the chart, will permeate, and sometimes rapidly, because that path is very short. So if you're using a fluid that has a tendency to permeate, if you're using a sealing method or material O-ring that allows rapid permeation, it could be something to consider given the applications. O-rings also will not generate a high degree of sealing force. They deform rather easily, but that can be an issue at much higher pressures, right? You can't expect an O-ring to be able to deal with the types of stresses that you would expect from some other technologies. And then finally, there is actually a bit of a corrosion concern with certain O-ring fitting designs, where if there is an entrapment area based on the design of the fitting, you could have some corrosion concerns depending on the interaction of the fluid and the material of that connection. So when we look at O-ring fittings, they absolutely solve the problem of gaugeability. For lower pressure applications where the large sealing force isn't necessarily needed, they can be a good choice. They will absolutely, you should consider permeation for these types of connections. And in some cases, based on the design, keep an eye on the corrosion compatibility, especially if there's any sort of dead space or entrapment there. So we've talked a lot about gaugeability. We've talked a lot about permeation, right? So the first two types of connection technology will have some degree of permeation because they rely on whether it's a PTFE tape or some other method or an O-ring in order to achieve that sealing performance, right? So anytime you put a soft good in there, you're going to have some type of performance. So kind of the next shot at improving connections for fluid systems is what we'll call flare style fittings, right? So really what it does is it eliminates that soft good for sealing and relies on the interaction of two metal parts, namely a kind of cone and then a receiving part of that cone in a few different iterations you can see here to create that seal. So these can be gaugeable, just like the O-ring fittings, has a very short seal length. So if those seal areas are not made up correctly, you can get leakage across that seal because the length is so small. And additionally, there really isn't almost any opportunity for really solid flex support, which brings up issues around vibration resistance, right? So you have a short seal length that's a metal to metal seal. And if you imagine, Matt had described that a couple of the factors are not only the vibration intensity, but how far apart where that vibration is coming from. You have a long length and a high intensity can be a challenge for flare style fittings. But they do get rid of, improve on the O-ring and soft good sealing style designs and really work to eliminate that permeation, which can be very, very important in some instances. So what we're going to do is we'll actually stay on this kind of metal to metal flare-ish style connections for just a bit and then revisit our table in a few slides because they're all kind of variations on the same theme of that interaction of two metal parts creating a seal through burnishing. So the next is what we call diesel style fittings. Same concept as a flare fitting. But it is what we call like a manipulated end on the tubing. So the tubing is actually manipulated to give you your cone and create that flare to mate in with the other part. It's a difference with these than a traditional flare is these are largely considered blowout proof because you've got that manipulated end in the tubing, which depending on your design can provide blowout protection. But the same as traditional flared fittings, they're very susceptible to a lot of vibrations, right? Particularly the high vibration scenarios. That being said, we talked about sealing forces with O-rings being relatively low because we're talking about two metal bits coming together and creating that seal. The sealing forces are relatively high and can be used successfully for higher pressures, right? So you kind of see it here coming from the diesel fuel rails where those can get up to 30 plus KSI. In a lot of times. So that's the diesel style fittings. Again, another flavor of the flare style. And then the third and final, which is also a very common connection within the high pressure space is cone and thread. So similar to diesel style fittings, these rely on the tubing being, in this case, machined, not manipulated, but machined, to create a thread and a cone on that tubing, which then is paired with a collar and a gland, and then your fitting body. So a relatively complex connection of parts, but it does give you that same style connection of the interference of two metal parts, which gives the short sealing length, high sealing force, even higher than the diesel or traditional flares, which enables these to perform at very, very high pressures. Now, what I will say about both the diesel style and cone and thread fittings is that because these rely on manipulated ends of the actual tubing, there's almost always some special equipment that's needed. So what you see here is really a traditional kit for coning and threading in the field. So if you're stick building systems, that can be another layer of assembly challenge that you would have, just making sure the operators are fully trained up on how that equipment is to be used, how to check for proper manipulation of the tube or machining of the tube. So it's a nuance in these higher pressure fittings that should be considered. And again, cone and thread, like the diesel style fittings, is susceptible to vibration when you're looking at the factors of a connection. So I want to jump back one slide and mention, because you'll see it in the chart that we put up, that a lot of these higher pressure fittings incorporate a weep hole that allows users and operators to detect leakage, right? Very high pressures. You want to have some way to do that. But what it also does is it allows for an ingress path of any environmental factors that could potentially provide some corrosion of that base fitting material. So high pressure applications, particularly in offshore around a lot of marine environments, could be susceptible to that type of corrosion because there is that entrapment area. So if we look at the family of flare style fittings, really what we're talking about is a very short or non-existent permeation path, right? It's certainly a step above the taper thread and the O-rings. Sealing forces are pretty high, particularly in cone and thread. The area is small. A difficulty of assembly, particularly with diesel and cone and thread, because they are manipulated ends. So there's some special equipment and training required. None of these fittings that we've talked about so far have great flex support. So they are going to be susceptible to vibration in those kinds of applications. And then, cone and thread and flare with the weep holes can certainly pose an issue for corrosion if you're using them in an area where that can be a problem. So kind of the first iteration was, how do we solve this permeation issue, right? And then, the next step really is, we think we've got that figured out. How do we improve our flex support? That's the one thing across the board that really none of these connections can offer. And the first shot at that is a single ferrule, what we call a bite style fitting. So that uses a single ferrule that bites into the tubing. There's high sealing force when the nut drives that ferrule against the body and then ultimately into the tubing. It does improve the vibration performance as compared to some of the other style connections we've talked about. It's also gaugeable. So that maintains the gaugeability of something like an O-ring style fitting, while also improving on the flex support and really minimizing any sort of entrapment areas for corrosion. Now, what the single ferrule does is it does create, with that high force, it does create a stress riser right there on the tubing, which means that while it does improve the vibration performance, it doesn't really get to a full vibration support that we would like to see in those kinds of environments, along with the low permeation and sealing force factors that Matt had talked about. So finally, before I hand it back off to Matt to go through the Swagelok technology, I do want to talk about kind of the final iteration of these connections, which is a 2-ferrule style fitting. And I'll hit the highlights here. You'll hear much more about it from Matt, but the 2-ferrule style adds an additional ferrule, which really improves the support of that connection and consequently its ability to resist vibration. It also decouples the job that the front ferrule has to do from doing everything in terms of holding the tubing and creating those seals to really being focused on the seal. It remains a gaugeable design, and that front ferrule, because it can be designed to do that sealing, does give you a much longer seal length than a single ferrule would, because it has to do all those things at once. So the 2-ferrule style is sort of the end of the evolution we'll talk about here, and does offer a short or non-existent permeation path, high sealing forces, better sealing area. So really it's only second to, if you remember the taper thread discussion we had at the beginning, where that's a really long leak path. The 2-ferrule design is really second only to that very long tapered thread sealing area. These fittings are gaugeable. They provide strong flex support and minimal corrosion opportunity from the fittings. So with that, I'll hand it over to Matt to really dive into that kind of technology before we wrap up for the day.
All right, sounds good. Thank you so much, John. Hopefully you guys can see and hear me again. What we're going to talk about this next one is actually Swagelok's tube fitting technology in that 2-ferrule space. As John mentioned before, 2-ferrule fittings provide really good, robust product performance. Swagelok does a really great job in gas seal, as well as vibration resistance due to the tube grip that we're seeing. And the way that we make this easier for people to install is you have a straightforward assembly process by 1 1/4 turns. It's gaugeable because it's a position-based assembly process. You can have a gaugeable surface between the nut and body that you can use like some kind of tool for to maintain that the installation is proper. We also provide tooling to make assembly easier, whether that's pre-swage, gaugeable tools, and others. I really want to move into the kind of the next statement of what makes Swagelok's tube fitting so good in the vibration performance. And that really comes down to some of our technology that we have created in our back ferrule. We have what we call a SOUT 12 surface carburization, and that's a low temperature carburization. It creates tool steel-like hardness, so it enhances corrosion resistance and improves wear resistance. But because that like white outer layer along the ferrule that you see there, it's only on that surface of the ferrule, which means you may retain the ductility of the underlying material. So that means you can get a really nice bite onto the tubing, but you are able to provide a ductile surface that the back ferrule can actually rest onto the tubing and kind of protect that stress riser that happens when you bite into tubing. So that's what we'll kind of go to next, is that back ferrule that Swagelok has designed, what we call is our advanced geometry. It hinges and collets. The hinging and colleting action, it actually occurs where that bite point is at on the back ferrule. You get that bite area there at the nose of the back ferrule. And as you go further upward along that back ferrule, you see that there's that surface that's kind of just made it up right against the tube. So imagine you have a vibration load coming from that top of the slide down the tubing towards that back ferrule. It's going to hit that colliding region first. And that's really what that's going to do is create a dampening type effect in the back ferrule. So you're protecting the stress riser and the rest of the fitting technology from that vibration load, which means you're going to get really great vibration resistance and tube support in that fitting technology. With our back ferrule design, it does create a really great gas tight seal. And it also enables us to get pretty consistent remakes as you go through its life cycle. And as I mentioned prior, that there is a gaugeable surface between the nut and body. That really makes it easier for the end user, so you can make sure that your fitting is pulled up properly. And that's kind of the Swagelok tube fitting technology. What we'll want to do is just kind of go through, give you another summary. So some of the things you have to keep in mind when selecting the fitting technology for your applications is how much vibration or flex will the fitting experience? How important is safety to this installation? Is permeation a concern? Like we mentioned before, those kind of materials, like when you're using O-rings and stuff, you might get a little bit more permeation going through your fitting technology. And then how likely will corrosion occur from the environment or system media? We want to make sure you minimize those internal and external surfaces that can have the corrosive media just sit in those zones. The next one is even the highest quality production with the wrong fitting technology can result in a poor outcome. So you might have say your taper thread connection and everything, and you put it into a vibration heavy and it might not survive those kind of things. And then lastly, so with more advanced fitting technologies, typically the price is a little bit higher, but in most cases, you're going to have a safer environment and overall your cost of ownership is going to be lower as well because you're not having to replace fittings as they fail as you're going along. And with that, I think that's the end for us and just for some learn more.
Excellent. Thanks very much, Matt. A few of you have already submitted questions, so we're going to jump right in. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. So let's see. How does a tapered thread design How does a tapered thread design protect against corrosion?
So I'll take that one, Chris. Really what that comes down to is when you're pulling up a tapered thread connection, you usually use PTFE tape or some other kind of sealant on it. And it really comes down to if you wrap that tape around that male thread really, really well and it covers all of the threads, you minimize the entrapment space that you would have. So if you end up actually having, if you don't end up using that PTFE tape there, you actually, that like green circle that we had in the table really goes down pretty quickly because you have the ability for that corrosive media to actually enter into those threads and it creates a problem at that point in time.
Great, thank you. Someone else asks, are there recommendations for tubing support distances or materials, i.e. vibration fatigue?
Yeah, Matt, if you want, I can take this one.
Go for it.
Great. So there are, and there are some resources that Swagelok's got out there. The full tube fitters manual has a couple tables. There's a pocket guide that I think contains the same. And really the recommendations are based on tubing size. So 1/2-inch tubing every 5 feet, 1-inch tubing every 7 feet, right? So it depends on the tubing sizes. And then in terms of materials, there's a couple of things to think about. One is, obviously make sure whatever clamp material you're using plays nice with the tubing material. But then also think through any of those entrapment areas that could exist with a tubing clamp. If there is an area where that environment, anything in the environment could collect and settle and maintain itself against that tubing, you could end up actually with not a vibration concern, but more of a corrosion concern. So certainly I would say there are great resources on Swagelok.com. You can find both of those, Tube Fitter's Manual and the Pocket Guide, with extensive tables based on tubing size. And then also just think through the entrapment areas that could exist in a tubing clamp to make sure you don't inadvertently run into a long-term corrosion issue while solving the vibration problem.
All right. Could you describe again what makes a fitting gaugeable and why that is important?
Matt, you want to take that one or should I?
You go for it, John.
Okay. So a gaugeable tube fitting is one that can be, the makeup of the fitting can be identified using a relatively simple gauge or tool. Right. And generally what you need for a gaugeable fitting is one that is kind of position oriented from a design perspective. And I'm sure I butchered that. So Matt, feel free to course correct where needed. But effectively, if you're pulling up a fitting that as it moves and advances along the threads, that's what drives the connection to be made up correctly. That's a very easy fitting to gauge or make gaugeable, I should say. Whereas something like an NPT, while it does advance down the tapered threads, it's not designed with a particular position in mind of being fully made up. So it's very difficult to create a gaugeable tapered thread. Matt, anything else from the design perspective that you'd like to add?
No, that was pretty good coverage.
Great.
Excellent. Digging into a little more detail, somebody asked, if I were to use a different alloy tube with a stainless steel fitting, is the tube fitting still rated for up to the tube design pressure?
I'll take that one, John.
Great.
Yeah, so that's a great question. In general, what we'll call that is a engineered combination, since you're using a different alloy tubing with stainless steel fitting. Swagelok does numerous testing on those kind of engineered combinations to ensure that the design pressure is correct. We offer some guidance on what those are. So we have our own engineered combinations catalog that lists out the various different alloys that can be used. And usually the tubing design pressure, that rating, is based on the tubing. So it can differ slightly from tubing to tubing material, even though the fitting is staying the same.
Yep. And just to add on to that briefly, you can find all of the engineered combinations that Swagelok has done testing on and provides ratings for in a aptly named Swagelok Engineered Combinations catalog. So that's another resource you can find on .com if you want to dig into which material combinations have been tested and really put through their paces by Matt and all the other folks on the engineering side of the house.
Great, thank you. All right. So someone asked, if I were to use that's one we just did, which O-ring seal and seal materials would you recommend for carbon dioxide valves that interface with the atmosphere, such as interrelief valves?
Yeah, I can take this one, Matt.
Please do.
So that's a difficult application for sure. We've had some experience with a variety of different compounds. Hydrometer bunas seem to work well. What I would suggest is certainly engage your local Swagelok team, your local Swagelok field engineer who can help really dive into that specific application and help talk through a little bit like we did today of what are the options, where are the benefits of choosing one versus another, where are the drawbacks, because that's a tough application when you're talking about carbon dioxide, immediately going from what I'm assuming would be pressure down to atmosphere. That can be tough. So while I say we have had some success with some of those materials, I would encourage you to contact your local Swagelok sales and service center, and they'll be able to connect you with their field engineering team who is plugged into our broader field engineering network and can help talk through that application in more detail.
Excellent. And one more to wrap things up. Why is the use of grease a concern when creating a seal within a fitting?
Yeah, I'll take that one, John. So I briefly mentioned earlier about like sealing forces in that kind of slide. And where it comes down to is if you have very minimal force, sometimes people will like to use a grease. What really gets hindered there is that grease over time will wear away. So like for your system media that's coming into contacting with it, it'll slowly chip away at that. So over time, you're going to see that grease is removed, and you're not going to have any leaks at the very beginning of that, but over time you will see leakage start to happen, and you'll have to remake that fitting back up, and it just has downtime with your systems.
Okay. And actually, we do have another question. Is your FKO double ferrule?
I'll take that one too, John. Yeah, our FK technology is a double ferrule design. It's a female style instead of like the male style that you saw here in our presentation. So it's like, but it does have a double ferrule design.
Okay, excellent. And that's a wrap. We really enjoyed having you guys here today, so thanks very much. That concludes today's presentation. And on behalf of Oil and Gas Journal, I'd like to thank Swagelok for sponsoring today's webinar. And of course, thank all of you for being here. Have a great rest of your day.